Start my today's session with again this mathematical tool of moment generating function, and my today's main topic which I want to discuss is about evaluation of statistical parameters of normal distribution. Yesterday I discussed the evaluation of the statistical parameters for binomial and Peugeot. Today is the time for normal to come into the picture. So for this evaluation of statistical parameter, I am again going to take the help of this wonderful mathematical tool, which is called moment generating function. And once again, I'm repeating that moment generating function for the random variable capital X when X is discrete is defined as the term, it is defined as e to the power tx multiplied by the probability density mass function preceded by a summation sign over all possible values of x. And if capital X is continuous, its moment generating function is defined as expectation of e to the power t into capital X, which is the integration over the entire real line of the integrand e to the power tx multiplied by the corresponding probability density. Our first problem of today's class is about to find the moment generating function of the normal distribution, and accordingly and subsequently we are going to deduce the statistical parameters. You already know that the statistical parameters corresponding to the normal distribution is mean, mu, and variance sigma, sigma square, or sometimes we call that normal distribution, the particular random variable is normal variate if it has mean, mu, and standard deviation sigma. Both things are same. So here we are going to discuss all about this with from the viewpoint of moment generating function. Now, first of all, we shall discuss about normal variate, and later we shall discuss about standard normal variate. Now, if a variate is normal, you already know that its moment generating function is defined as this: fx equal to 1 by sigma root 2 pi e to the power minus half x minus mu by sigma whole square. That is the form of the moment generating function. And x is lying between minus infinity and plus infinity. Average is lying between minus infinity and plus infinity, and standard deviation is always positive because it is the measure of dispersion or measure of distance. Therefore, by the definition, the moment generating function of the normal variate is defined as mxt is equal to integration over the entire real line, that is from minus infinity to plus infinity. Just correlate e to the power tx, okay? And in place of fx, I'm substituting this probability density function. Now I'm going to integrate with the help of method of substitution, and the first substitution which I'm going to make is this. In place of x, I'm going to substitute z with the transformation given as z equal to x minus mu by sigma. This transformation is often called the change of origin and scale. So if z equal to x minus mu by sigma, and since sigma is constant, mu is constant, so dz will be dx only, 1 by sigma multiplied by dx, okay? So therefore, I'm going to substitute that over here. Now, first of all, you see, I'm going very slowly. 1 by root 2 pi is the constant term which can be taken outside the summation sign. And in place of e to the power tx, I'm writing e to the power t, since z equal to x minus mu by sigma, that will be sigma z plus mu. And since x minus mu by sigma is z, I'm substituting z in place of that, and we are going to get e to the power minus half z squared. And since 1 by sigma into dx is dz, so I'm substituting dz over here. Now you see, if I break this into two halves, we get e to the power t sigma z and e to the power mu t. I have to do a little bit of adjustment here. In e to the power t sigma z, z is involved. So we cannot take this quantity outside the integration sign because it is dependent on z. That should be integrated with respect to z. But e to the power mu t is constant, and that can be taken outside the summation sign. And hence we are getting e to the power mu t into 1 by root over 2 pi integration minus infinity to infinity e to the power t sigma z minus half z square dz. Now I have to do a little bit of mathematics here. So I'm keeping this term as same e to the power mu t by multiplied by 1 upon root over 2 pi. Integration minus infinity to plus infinity. I am now taking this adjustment is kind of a mathematical trick. What I am doing is that I am taking minus half outside the summation sign. The immediate, the instant idea of adjustment would have been to take z outside the summation, to take z common from this expression, but that will not work because I want some kind of perfect square here in terms of z. That is the objective, and keeping that objective in mind, I'm taking minus half outside the summation, and therefore consequently this becomes z square minus twice t sigma z. So to get a perfect square, one term is still missing. And you very well know what is it. If I have z square, I have 2z, and this term is present, t sigma. So I need a term like t sigma whole square. Okay. So in the next step, I am doing that. I am adding sigma t whole square. And since I am adding this quantity to balance the system, I am at the same time subtracting sigma t square from this so that the ultimate result remains same. And therefore you see the first expression is becoming a perfect square. So we can write it as e to the power mu t. And you see one another thing you see. If I multiply by half now, what will I get? I shall get minus half multiplied by minus sigma t whole square. That will be e to the power half sigma t whole square. Okay. So again, I can break this exponent into two parts. E to the power minus half of this into e to the power minus half of that. And from the second one, I am getting half sigma square t square. And that is being taken outside the integration sign. And therefore, we are going to get e to the power mu t half sigma square t square. One printing mistake is there. I beg pardon for this. I didn't see it earlier. 1 by root 2 pi isn't present, but here 1 by root 2 pi will remain there. 1 by root 2 pi will not cancel. 1 by root 2 pi is still there. I just missed it somehow. So 1 by root over 2 pi, if you are noting my, what I'm saying, that make this correction, or you make a point of it so that you can later correct it. Before uploading the note, I'll correct this particular section. So 1 by root over twice pi will be there, and integration minus infinity into infinity e to the power minus half z minus sigma t whole square dz. My next substitution will be to put z in place of z minus sigma t, another variable u. So I'm putting here. So we'll get e to the power mu t plus half sigma square t square 1 by root over 2 pi integration minus infinity to plus infinity e to the power minus half u square du. Okay, because since z minus sigma t is equal to u and t is constant, sigma is constant, so dz will be du. And therefore, this particular thing, 1 by root 2 pi will be preceded by 1 upon root over 2 pi. That entire thing will be what? The total probability. And total probability is 1. And therefore, the moment generating function of the normal variate mxt comes out to be e to the power mu t plus half sigma square t square. This is a very well-known result, and you have to memorize this result for further calculation and as well as for further applications in whenever necessary. Once moment generating function is found, our next objective is to get mean and variance for the distribution. So we are going to take the derivative of this with respect to t once first, putting t equal to 0. And if I do so, we get mx 0 prime, that will be mu1 prime. And mu1 prime is nothing but the expectation of the random variable capital X. And if you take the derivative of that, you check it by yourself, okay? That will be e to the power mu t plus half sigma square t square multiplied by mu plus sigma square t. Okay, because for t square there will be a twice t term, and that two twos will cancel each other. At this point, we are substituting t equal to 0 in the expression, and we are going to get mu. So mx prime 0 becomes mu. Okay, and mx prime 0 is nothing but the expectation of the random variable. So the mean has been found from the moment generating function of the variable, normal variate. To find the variance of the normal variate, we are going to take the double derivative of this expression. Taking double derivative of this expression is same as taking first derivative of that expression. Okay, so we are going to write it as this. Mx double prime at the point t equal to 0 will be mx double prime 0, double derivative of mxt at t equal to 0 is same as mu2 prime, which is nothing but e of x squared. And after taking the derivative of this clumsy expression, we are going to get another clumsy expression like this. Okay, you are supposed to check it by yourself. So we get this this as double derivative of the moment generating function of the normal variate. And after this, we are putting t equal to 0. After that, we are putting t equal to 0, and if I do so, if I put t equal to 0 in the relevant portions, we will get mu square plus sigma square. That is the expectation of the random variable squared. And thus the variance of x will be expectation of x square minus ex whole square, which will be mu square plus sigma square minus mu square, which is sigma square. And you know, this is telling with what we knew about the normal variate, that normal variate has mean mu and variance sigma square. This is actually coming out from this expression. This is coming out of this expression. Okay. Here I have made two practice problem for you. I have put two practice problems for you to practice. One, both these problems you carefully observe. In the first problem, you are supposed to find the moment generating function of the rectangular distribution of continuous form, or which is sometimes known as continuous uniform distribution, and hence you are supposed to find its mean and variance. Second is the moment you are supposed to find moment generating function of the exponential distribution, and hence its mean and variance. Both these probability distributions are actually known to you. Rectangular distributions is known to you. You have done the problem. You have also solved problems in the examination. Exponential distribution is also known to you, and you know very well that exponential distribution is also a special case of gamma distribution. So you try to solve these two problems. It is my request. Okay, just practice for practice purpose. If you find any difficulties in calculation, you always can ping me. Now we are going to discuss some of the properties of the moment generating function. These properties are very important for solving problems. First of all, I will try to say to you the meaning of these properties. What is written here, you say, the property is expressed in terms of a theorem. The theorem says, if small a and small b are constants, then we have the following results. What are the results? M of x plus a of t is equal to e to the power at mxt. What does it mean? If I give a linear transformation of the variable capital X to the point A, or if I change the origin from 0 to A, then, or if I give a linear shift to the variable capital X, then moment generating function of this becomes e to the power at multiplied by moment generating function of the original random variable. If I change the slope of the random variable x as bx, the moment generating function of this will be moment generating function of x with respect to the new parameter vt. And the moment generating function takes this particular form when we give a change of origin and scale shifting to the variable capital X. So m of x plus a by bt becomes e to the power a by bt multiplied by mx of this parameter t by b. T by B, what does it mean? The parameter time is being divided by B. Or you can say the parameter time is being divided by several parts. Okay, if B equals to 2, parameter time is divided into 2 halves. If I am talking about 1 hour, T by B, T by 2 represents first 30 minutes and second 30 minutes. Try to think like that. Okay. These properties of the norm, these properties of moment generating function are so important that now you're going to see that how we can use it to evaluate the moment generating function of the standard normal variable and consequently its mean and variance. But these expressions are also very confusing because suddenly if you ask me, I'm the teacher, but if you ask me that, sir, what is moment generating function when capital X is shifted by A and its origin is shifted to B, A and scale is changed to B, then probably I shall fail to give you the proper answer. Because, but if I know the mathematics, if I know how these results come, I will tell you, hold on a minute, I'm going to tell you, I'm going to calculate and I'm going to tell you what will be the expression. So I'm here showing you these simple proofs. So you just don't panic, okay? First of all, I'm writing this, m of x plus a of t. You see, I'm simply using the definition of the moment generating function, but the variable is now considered as capital X plus a. So you know moment generating function mxt is e to the power expectation of e to the power tx. Here in place of x, I'm putting x plus a. I'm breaking the exponent into 2 parts, e to the power tx into e to the power ta. But you know that if a constant is present inside the expectation sign, it can be taken outside. So e to the power at is a constant. It is being taken outside the expectation sign. And therefore, I'm getting e to the power ta, expectation of e to the power t multiplied by the random variable x. See how easy it becomes. And e to the power at remains same. And this is the definition of mxt. So this result can be found out. No need to memorize this result. Okay, whenever you'll be needing this, you just do this quick mathematics. Just like that, we can do the second 2 quick mathematics like this. M of bxt, it is far more easier than the previous one. I'm writing it as expectation of e to the power t multiplied by b into capital X. Now, I am just doing a little bit of trick. I'm going to apply a little bit of trick here. I'm putting this t and b together and I'm writing expectation of e to the power bt multiplied by x. And what will be that? If expectation of e to the power tx is mxt, so expectation of e to the power btx will be mxbt. So I'm writing this. See how easy? And when I'm doing this, what am I doing over here? I am writing the definition in terms of the variable x plus a by b. So m of x plus a by b t becomes expectation of e to the power t multiplied by this variable x plus a by b. I am breaking it into 2 parts, a by b into t and t by b into capital X. Now the exponent is breaking into 2 halves, e to the power a by b into t, e to the power t by b into capital X, okay? And now you know that the exponent e to the power a by b into t is a constant quantity, and therefore it comes out of the expectation sign and it becomes e to the power a by t multiplied by the expectation of e to the power t by b into capital X. And here in place of t, we have t by b. So I'm writing it as e to the power a by b into t mx t by b. Don't try to memorize the left hand side and the right hand side. Don't. Try to remember the mathematics. Remembering mathematics will be far more easier than to remember the result. Now you can ask me, why have you done this suddenly? Why have you done this particular mathematics on the properties of moment generating function? Because of the evaluation of statistical parameters of the standard normal variate. Now, if we consider this property 3 of the moment generating function, you again see that if I put a equals to, in place of a, if I put mu, minus mu, and in place of b, if we put b equal to sigma, then we are going to get m of x minus mu by sigma. In place of A by B, I'm going to get minus mu by sigma into T. And in place of T by B, I'm going to get T by sigma. Now you know that X minus mu by sigma is nothing but Z. So I'm writing here MZT. E to the power minus mu by sigma into T remains same. And here I'm writing mx T by sigma. But the moment generating function of the normal variate has already been found out. The moment generating function of the normal variate is what? E to the power mu T plus half sigma square T square. Okay, this is the expression. See carefully, this is the expression of the moment generating function of the normal variate. Okay, where with parameter T. So if I use this, if I apply this over here, the moment generating function of T by sigma will be e to the power mu T. In place of mu T, I shall write mu T by sigma, half sigma square T square. So I'm writing here half T by sigma whole square, sigma square by 2. And here I am actually, that was half T square sigma square. See, this 2 is also misplaced. I have written 2 twice over here. That is a printing mistake. Only 1 2 will remain, because you see half T square sigma square. Only sigma square will be there. And in place of T, there will be T by sigma whole square. Okay, otherwise mathematics will not be all right. So you make this note quickly in your copy. So this will not be sigma square by 2. This will be sigma square only. Now, if I do so, then this sigma square and this sigma square will cancel each other. And we can break this exponent into 2 parts. You can write e to the power mu by T, mu into T by sigma into multiplied by e to the power half T square by sigma square into sigma square. Now this expression and that expression taken together will give you e to the power 0, e to the power minus mu by sigma into T plus mu to the power sigma, mu T by sigma. Okay, so that will be 0, e to the power 0, that is 1. And here sigma square and sigma square will cancel each other. That will be exponent of T square by 2. So we have found that moment generating function of the standard normal variate capital Z is having the expression e to the power T square by 2. Now to find the mean, we are going to take the derivative of that with respect to T once first and putting T equal to 0. So just like my previous calculation, it becomes mz0 prime. And the derivative of this becomes half of e to the power T square by 2 multiplied by twice T. We are putting T equal to 0 over here, and the result is 0, which is expectation of Z. And when I am taking the double derivative of this expression or the single derivative of this expression, mz double prime 0 becomes d dt of this expression. The derivative is taking this form. You check the calculation by yourself. Okay, because you have seen that I am very much prone to silly mistakes. So you do the calculation by your own and put T equal to 0. If you do so, you will find that result 1 will come out. And that is what? mz double prime 0 is nothing but Ez square by definition. And correspondingly, Vz will be Ez square minus Ez whole square, which is equal to 1 minus 0 square, that is 1. So variance of Z is 1 and expectation of Z is 0. And you already know that, you already knew this, that if we talk about the standard normal variate, the variance is 1 and standard deviation is 1 and mean is 0. That means origin is shifted to, the mean is shifted to origin. We have done so many problems also in previous classes. So I have put a definition over here. This definition is very important and you try to remember this definition. Okay, the definition goes like this. If the random variable capital X has the mean mu and standard deviation sigma, the random variable capital Z, whose values are related to those of capital X by means of the equation Z equal to X minus mu by sigma, has expectation of Z equal to 0 and variance of Z equals to 1. A distribution that has mean 0 and the variance 1 is said Sorry for this sudden interruption. There was a dip in the network, so that happened. Okay, don't worry, I'm almost done with today's class. So anyways, what I was saying, that a distribution that has mean 0 and variance 1 is said to be in the standard form, and when we perform the above change of variable, we are said to be standardizing the distribution capital X. Now you see what this definition is saying. This definition is not talking about, in this definition, I have never used the word normal variate, or I have never used the word standard normal variate. Rather, I have simply used the word random variable. So the definition says that, it don't say that this definition corresponds to normal variate. The definition says that if you have any variable capital X, if you have any random variable capital X, this may be discrete also, or any continuous also. Then if you give a shift like this to the random variable capital X, a shift like this, and if you can show that after giving a shift like this, the mean of the new variable is 0 and variance of the new variable is 1, then we say that standard form of that random variable X has been obtained. It can be any variable, not normal. So it's very important result. Okay, and normal distribution, normal variable and standard normal variable is a special case of this definition. Okay, remember this. And if I do so, if I give a transformation like this to the variable capital X, that is transforming, that kind of transformation, shifting of origin and scale, that kind of transformation and doing this kind of mathematics means I am standardizing the distribution of capital X. This is called standardization. Remember the word, remember this term, standardization. Now I have put here a chart for the sake of your purpose, and in this chart I have shown you several distributions, probabilistic distributions, along with their parameters, their moment generating function, their mean and their variance. Wonderful will be thing if a particular student can remember all entire chart. That his remembering power is great. My remembering power is not that great. So what I shall only try to remember this expression, this particular column, that I shouldn't forget the probability mass function or probability density function, so that I can calculate the column 3, 4, and 5 by myself. That is my, it is what I want, I do. But if a student can remember this, then it is a wonderful thing. So here I have started with a discrete uniform distribution. Discrete uniform distribution is a kind of distribution which you have been doing from your school days. The probability of coin tossing, the probability of getting head and tail after coin tossing, probability of getting 1, 2, 3, 4, 5, 6 after dice throwing, probability of getting 52 cards after card throwing, all fall into this category. And therefore it has been written as 1 by n, probability is 1 by n for equally likely outcomes. And here the parameter is n, because if n is the total number of outcome is known, then the probability distribution is known. So if you try to find the moment generating function of this result will come out. And after derivating this once, twice, putting t equal to 0, mean will be of this form and variance will be of this form. Second is called Bernoulli distribution. Bernoulli distribution is a special kind of distribution where you see the n is not there. It's a special kind of distribution where n equals to 1. So here I am writing it as probability of x equal to small x. Here parameter is simply p. Okay, so it is represented as p to the power x into 1 minus p whole thing to the power x, 1 minus x. X is having only two values, 0 and 1. Moment generating function is q plus p e to the power t, and the mean is p and variance is pq. If you can recall Bernoulli distribution, then it is easy to recall the binomial distribution too. In binomial distribution, the thing is getting multiplied by NCX. In case of mean, P is being multiplied by N, variance, PQ is being multiplied by N, and Q plus P to the power T whole is raised to the power N. This calculation I have shown in my previous class. Poisson distribution, you already know, I have shown this in my previous class. Another distribution is there, it is called geometric distribution. It is of this particular form. Here the parameter is small p only, and the moment generating function is defined as denoted by p by 1 minus q into e to the power t. Its mean is q by p, its variance is q by p square. Just now I have shown you what normal distributions, what will be the moment generating function for normal distribution and the mean and variance, and what will be the moment generating function for the standard normal distribution and the corresponding mean and variance. These two are continuous uniform or rectangular distribution and exponential distribution. Wow, I have already shown you what will be the moment generating function. Okay, so the next thing only, I have shown you that I have put a practice problem for the sake of your practice, but I somehow helped you by showing you the result. Your next job is to verify whether these results are coming or not. So for exponential distribution, the moment generating function will be of the form 1 minus t by theta whole thing to the power minus 1. Mean is already known to you. It is a plus b by 2, and it is b minus a by whole square by 12. For continuous uniform, that will be e to the power bt minus e to the power at by t into b minus a, t not equal to 0. And the corresponding mean will be 1 by theta, and one variance will be 1 by theta square. And lastly, I have shown that the gamma distribution, where this expression is also known to you. We have done calculations, and you see one interesting thing is that this is the moment generating function, and one interesting thing is that the mean and variance of the gamma distribution is also same. The mean and variance of the gamma distribution are also same. So for discrete case, when it is Poisson, then mean and variance are same. For continuous case, when it is gamma, the mean and variance are same. Okay, so this mean and variance being same can happen for Poisson discrete distribution also, or can happen for continuous distribution also. Apart from this distribution, some other distributions are also there which have not been mentioned in the chart. There is Cauchy distribution, there is beta distribution, there is hypergeometric distribution, there is negative binomial distribution, there is log normal distribution. Many distributions are there, but I have skipped for the time being. Okay, if you find it interesting, you can you can see it in John Foynt's book. You can do, if you have found it interesting, you can do the calculation by yourself. No hard and fast. I'm not saying that you shouldn't do this because it is not there in the syllabus. This kind of thing I will never say. If you find it interesting, you can always try with those. But what is the utility of that? Often in engineering courses, we deal with different kinds of probability distributions. Some unknown and some known, mostly unknown. And if you have to tackle with the unknown distribution, unknown probability distribution, then to know its mean and variance, you can take the help of the moment generating function. So moment generating function is very wonderful tool, and it helps us in many ways. So my time is already running out, and it will be the class will get the session will be cancelled after the time is not being shown to me, but session will cancel very soon. So here with this, I'm going to conclude my today's class. Before uploading the note to the Google Classroom, I shall rectify the silly mistakes which I have done. And then if I can upload the video today, then I'm going to upload it in Google Classroom also, the link. And for the tomorrow, there will be no statistics class. You enjoy, and we shall again meet on Monday with the further topics of this particular section, basic statistics of module 4. So till then, ciao.